course one. And we should give extra credit to the 2 students not here.
Okay.
I don't think either of you are taking it for credits.
No.
There are only 2 students.
Okay, well, good afternoon and welcome to the Simon's Electron Microscopy Center's Winter EM course. Today's lecturer is Bill Rice, our EM manager and senior scientist here at NYSBC. Today's topic begins the third modality of EM that we're covering, and that's on crystallography as well as helical reconstructions. So that's really concerning any macromolecular structure that you can form an ordered array with. MicroED has gained a lot of popularity in the past few weeks and months because of its extended applications, in particular looking at small molecules. The highest resolution structure from EM is coming from a peptide solved by MicroED, and that's sub-angstrom. It's like roughly, I don't think it's published, but it should be around 0.7 angstroms. Our lecturer today, Bill Rice.
Hi. So as Ed said, I'll talk about MicroED today. So this technique has become quite popular just recently. It was actually runner-up for Science's 2018 Breakthrough of the Year, even though it's been around for a couple of years. But the reason, I'll go over the reason, but basically the reason is you can now chemists can more easily solve structures of their small molecules by using a non-high-end electron microscope, so a standard electron microscope that a lot of labs might have. You can now use this technique of MicroED to get the structure quite quickly instead of having to crystallize it and go to a beamline or even a local source to do X-ray diffraction.
So why do they put them on holy carbon? Why don't just continuous carbon be done with it, holes aren't useful, right?
Yeah, I don't know why, because this is true. This is done, these pictures are at room temperature, so the holes aren't actually useful. It might just be they have a lot of quantifoil grids.
Yeah.
Or
I mean, have some plain carbon.
We used, when we did it on, we were doing it on C-flat grids, which are holy, but they're thin. So I guess if you use a C-flat, you have nice thin carbon.
You might as well just make thin carbon. Anyway.
That's true, yeah. I don't see a reason for doing holy carbon, because you're not imaging ones that happen to be half over a hole and half not. You image the ones over carbon.
Continuous. You're just making it a lot harder. Anyway, curious.
Force of habit, I guess.
Yeah.
So in the course you've heard of several of the techniques. So for electron microscopy to get structures. So tomography, the best resolution I think is somewhere you can get between 3 and 10 from subtomogram averaging. If you're not doing subtomogram averaging, it's going to be worse than that. Single particle. This is the slide I used last year. So kind of X this out. So now it's less than one. The best resolution is now less than 1.8 angstroms. That's been published anyway. There's people who are going with apoferritin quite high, even beyond 1.8.
I think on Twitter 1.49.
1.49 on Twitter. I don't think Twitter counts as publishing yet.
Yeah, Twitter.
Yeah, 1.49. Yeah,
Don't be published.
on the cryo arm, but yeah. But on the other hand, those data sets are on Empire. So if anyone wants to download them, you can look on Empire and try your hand at it. For 2D electron crystallography, I believe it's still 1.9 angstrom resolution from aquaporin, but no one is really doing 2D electron crystallography anymore very much. But MicroED, this one gives you the best, which is the technique I'm talking about today, and it's sub-angstrom. So there are quite a few structures published at 0.9, 0.8 angstrom resolution for the 3D. So this actually will give you the highest resolution of any of the techniques. So these are some samples of structures which have been solved by this technique. So first of all, it was applied to a lot of different proteins. So it was done for catalase, lysozyme, proteinase K, calcium pump, and these all go to 2 to 3 angstrom resolution. Some of them a little bit better than 2, and then it's also been applied to small molecules. And first of all, it was applied to small. It was done It was applied to small peptides, and those ones were able to be solved to around 1 angstrom resolution, or even better now. So
there's no restriction as far as you know as to what it can be applied to. It could be anything at all.
I think anything, as long as you have small crystals. Yeah, the crystals has to be small enough for you to be imaged. But it's mostly been done of small things. So anything big, the thing is you still have to have a crystal. So if you you're going, I don't know, the main thing of EM is the special single particle. If you're above 50 kD now, you might as well do single particle, I would say.
But at first it all seemed to be doing with the amyloids and all these beta kind of things.
Yeah, I guess these.
Not true anymore.
Yeah, I mean, yeah, they did it. In the course we did it of catalase and proteinase K, or lysozyme and proteinase K. And I mean, I think they're quite. I guess the reason they were first doing on smaller proteins is because anything bigger you would just do. Why bother and just do single particle? Because then you're stuck with making a crystal again. So I was looking through the EMDB, I guess, the past couple of days, and sort of did a number of structures by year of deposition. So the first one was actually done in 2013, and then there are a few more in 2014. But if I looked in the EMDB, I guess those weren't yet deposited or something, or they might have been deposited after the fact. So when I look at the deposition data, I didn't actually see any, although they're pretty sure they're there. But the number of structures is growing. So 2015 there were 7, 2016 22, 2017 31, this is total number of structures. So 2015 7, 15, and then a bit of a dip in 9, 2017, and then 2018 there were 38. So it's quite a big jump in 1 year. And the main reason for this big jump in 2018 is this is when they got the idea of doing it for non-proteins, but for doing small molecules. Just looking at the overall statistics of it from the EMDB, 74% are single particle structures, and about 1% are listed as the technique of electrocrystallography. But that includes MicroED and standard, the old 2D crystallography. So about 69 of those are by MicroED, and about half of those are of small molecules, so less than 1 kb. So it does seem to be a technique which it is becoming more popular. People are talking about it. Chemists in particular are interested in it. I'm not sure if it's going to ever be a big thing for protein biochemists, because our aim of single particle is to sort of shrink things, be able to image things smaller rather than have to be forced to make crystals again. And this is another list of various structures that were solved. Generally, it's been, I don't think, there have been, apart from the small peptides and small molecules, the proteins that were solved aren't novel, but they were just sort of more sample structures that could be done. Sort of so far it's been a lot of it proof of concept. And then this is another list of sample structures. So this is the calcium pump. And for these, they had a paper in 2017 of this where they looked at this alpha synuclein from what they called invisible crystals. So it forms these tiny little needle-like crystals which you can't see by eye. It's in solution. And what they did was actually they just sort of took sort of a precipitate or something and then put it on a grid and then found crystals and were able to solve basically a 1 angstrom structure of it. So the technique has been proven to be quite powerful. They've also done amyloid, so these are mostly kind of beta sheet type structures, and that also has been solved to very high resolution using MicroED. So I guess in order to sort of explain how it works, I'll sort of talk a little bit about X-ray crystallography, because it's sort of the technique comes from it's a crystallographic technique. So the idea is you have your protein, which is arranged kind of in a 3D lattice of points. So that's what a crystal is. So the protein is all lying in the same position in a 3D lattice orientation, and you're hitting it with a coherent beam of X-rays or electrons, and sort of the beam hits it at an angle theta relative to the sort of the planes of the crystals. And then the planes themselves are separated by a distance d. And generally, you basically only get constructive interference from these X-rays hitting it when the path length difference keeps them sort of in phase. So this comes from Bragg's law of diffraction, which is n lambda equals 2d sine theta. So you sort of, I can't explain all of crystallography in one lecture, but basically, you only get diffraction at certain points, and you get certain discrete spots. If you think about it in terms of Fourier space, this is a 3D lattice. I'm just showing a 2D lattice, but the transform of that is another 2D lattice, and then it instead of being separated by d, the Fourier transform of it will be separated by 1/d. So it's all basically going back to Fourier space. It makes it kind of easier for me to think about it, how it works. So for X-ray to do X-ray diffraction, you basically mount a crystal. Generally, it's kept cold so that the beam you get less X-ray damage of it, and then you expose it to an X-ray beam, which is at a defined wavelength, and then you collect images of the reflections on a detector, and this is what one of the X-ray diffraction images looks like. The crystal is held this is basically the diffraction pattern of it. This is an image. This is the beam stop. So because most of the beam is not diffracted, it goes right through the crystal beam without being diffracted at all. So you get a very, very tight, very, very bright spot right in the middle. And so in order to not damage the detector, you have to put in a beam stop, and then that will sort of block out. The idea of it is it'll block out that zero undiffracted beam so that it doesn't destroy the detector. And of course, it's being physically held, so then you end up blocking out a little bit by the piece of metal that's holding it in place. And then what you get are all these little diffraction spots. And so what you collect actually are only the positions of the spots and their intensities. So you don't get the phase of it. So you remember the Fourier transform of anything all of the points will have an amplitude and a phase, but because we're collecting this sort of for real, all you get is the amplitude, or actually the square of the amplitude. So all you get is you don't have any sort of phase information. So from this you can't really in order to go back to do a back transform, you have to get the phases of it right. So that becomes that's the what's called the phase problem of X-ray crystallography. And also you have to rotate the crystal. I'll go into that next, but you have to rotate the crystal in order to get all of the reflections. So the crystal will be in one position, and then you'll get a diffraction pattern of what that looks like. You rotate it a little bit, you get another diffraction pattern, and you have to sort of rotate it through potentially up to like 180 degrees, but depending on the amount of symmetry, you have to keep rotating it in order to get a full diffraction pattern of it. And then once you have all of that, you basically use software in order to solve the phases and calculate the structure of the molecule itself that's in the crystal. So in order to solve the structure, in order to solve the phase problem, there are several different ways. There's what's called ab initio methods, and these are for small molecules, so say less than a kilodalton or something like that. You can use, basically there's software that will sort of help you sort of derive from scratch what the phases are. I suppose in a way you might say it's analogous to, you have to start with something, so it's analogous in our way. When we do single molecule or single particle reconstruction, we always have to start with some sort of initial model. We just start with some sort of blob or something that's roughly right, and then it eventually converges to it. I don't know exactly how the ab initio works, but I imagine it's something similar. It starts with some sort of initial guess, and then it figures out what the diffraction intensity should be, and then it converges on the right answer. But I guess it's quite a complicated problem, so it only works for smaller molecules. So you can't do it for something like a 30 kilodalton protein, I don't think. I'm not sure what the maximum number is, but I think it's probably around a few kilodaltons or something like that. It's not very
So
big.
these small organic crystals.
These small examples. Yeah, for something small like it's good enough. It works well. You also have to have high order diffraction, so I think better than 1.5 angstroms or so. Otherwise, the method also doesn't work. Probably can't converge. For real protein crystals, another way is to do what's called heavy atom derivatives. So you have your crystal, and you then soak in lead or some sort of heavy metal element into the crystal itself, and that you then get the diffraction of that, which is presumably that's lying along the lattice, and then from that you can get the initial phases and then work your way back. That's sort of what a sort of classical way, the original way of solving the phase problem for proteins. Then there's also MAD and SAD phasing, so this is like anomalous diffraction, so where you replace methionine with selenomethionine, and you sort of, I think they sort of tune the wavelength of it to sort of get, you sort of play tricks with the beam, especially at a synchrotron, to sort of get anomalous diffraction from certain elements which are in the cysteines, and then you get, that also helps solve the phase problem. And then finally, the most common way, I guess, is molecular replacement. So maybe you don't have the structure of your protein, but you have a structure of a similar protein, so you start with the phases of that, what the phases of that would be, and then work your way back and do it. But no matter what, when you just collect diffraction patterns, you always have this phase problem, and the phase problem has to be solved in order to get the structure. So I said that the crystal has to be sort of rotated, and so in order to get all of the diffraction spots, and that's kind of related to the idea of this, what's called the Ewald sphere, where you have, say, if you draw in 3D space, if you put your crystal somewhere, and then you draw a sphere around it with the radius of 1 over lambda, where lambda is the wavelength of the X-rays of the radiation that's hitting it, and all around your crystal is the sort of the 3D lattice from the crystal. You only see points which actually intersect with this Ewald sphere. So there would be sort of a whole array of points around this sphere, but you would only see the ones that happen to interact with the edges of the sphere, with the sphere itself. So in this case, this would be the 0, 0, 0 point, which is like the undiffracted beam.
Sorry, that's the high pressure freezer.
Right. And then this would be a diffracted point, and if this diffracted point happens to lie on this sphere of 1 over lambda, then you would observe it. Otherwise, you don't. And so this is sort of what the reciprocal lattice again would look like. So this is like 0, 0, 0. This would be the 1, 0, 0, minus 1, 0, 0 in this direction. So this sort of lattice is sort of existing in space, but what you actually collect on the X-ray pattern is only where this lattice interacts with this, hits the sphere. And so what you do is you rotate the crystal, which effectively rotates the lattice, and then if you rotate this, you can see that this point would move out of the sphere, and then this point would move into the sphere, and then you would observe different points. So as you rotate, basically, as you rotate the crystal itself, you're going to see a change in the diffraction pattern, and you'll get different spots, and the spots will appear and disappear as you rotate. And so what you do is when you rotate it, you sort of sweep out this area, and you'll collect all of these spots eventually. So that's why you sort of have to rotate the crystal while you or during the collection. Otherwise, you have to get different views. If you ever went to the tomography lecture, it's the same sort of thing, except we're sort of doing it in reciprocal space, where in order to get a 3D reconstruction, and if you're collecting images in real space, you have to collect you have to rotate it. Otherwise, you're only going to have one view, and you're not going to be able to get a 3D reconstruction. So what's actually done is instead of you can imagine one way of doing it would be to take a picture, have the crystal in a certain orientation, blast it with the X-ray, collect a diffraction pattern, rotate it, hit it again, rotate it, hit it again, and that you could get a whole bunch of still images like that. But that actually wouldn't kind of collect everything, because basically as you rotate it, you can imagine as you sort of move this sphere, points will sort of come in and out. And so if you rotate it a little bit, you might only collect half of the point. And then if you rotate it, say, another degree, you might be gone altogether. So there's sort of no guarantee you're hitting sort of the peak intensity of any of these points. And the main thing that you collect in diffraction is the intensities. So you have to have a very good, at the very least, a very good measure of the intensities of the diffraction pattern, because some spots will be more intense than others. So what's actually done is, for X-ray detectors is, as they image it, they oscillate it. So the image is sort of oscillating back and forth by a couple of degrees or a half a degree or something like that, as the beam is hitting it. And so then it's getting, if you could imagine if you oscillated this, the original EVOL sphere would be here in these solid lines, and then it gets rotated a little bit and everything gets moved up a little bit. But because you're rotating it as the data is being collected, it all gets sort of smeared out, and these sort of become what are called loon. Each point becomes what's called sort of a loon. So it sort of comes in and out and moves a little bit and becomes brighter and dark, less bright. And so that way you're not missing any information. So here's a sort of a sample where you have this would be an image which is taken at one particular angle, but this one is not being oscillated. And then if you rotate the crystal by 5 degrees and then oscillate it by half a degree, you get a change in the pattern. So some of the spots are still present, but other spots start showing up. So you sort of in this way they sort of collect. You sort of collect all of the diffraction data that's there by collecting it as it's rotating a little bit. So in X-ray they sort of rotate it, oscillate it as it's imaging, rotate it again, oscillate it as it's imaging, and this is all done automatically. I think now X-ray is virtually completely automated.
So you go 5 degrees and oscillate half a degree, so there's still many degrees not represented.
Well, I think this was just a sample, so I don't think in real life, they're not doing it in 5 degree increments, so they're probably doing it in 1 degree or something like that. They're filling in all of the space, but then each one it's not a continuous rotation, which is sort of what we'll be doing. They sort of rotate it and then oscillate it as it's imaging.
Why don't they do continuous?
I don't know. I don't know enough about X-ray.
I think now they do that with the Flask, so you just continuously rotate pretty fast, and then they just shoot. There's a few minutes and you get the whole crystal.
For
X-ray, right?
They do that?
Oh, they do it? They do it? Because I thought...
They do? Or they just like rotating and just open the shot?
Yeah, with the fast one.
It is super fast, so
Super fast,
it will
yeah.
take like a minute and a half
I guess it must be continuous, so you can't stop and stop.
Yeah.
Maybe this was from the days of film or something like
Yeah,
that.
but it's quite recent when they made it, with the new cameras, right? The Flask.
So, of course, we all know the limitations of X-ray crystallography are that a lot of them don't crystallize. A lot of proteins don't crystallize, or they don't crystallize to make proteins large enough for X-ray diffraction experiments. And then there's also X-ray electron lasers for small, tiny microcrystals, where you just blast the whole thing with it and get one pattern and that's it. But then you need many crystals, and you need. It's a very expensive experiment. There are many setups that have it. These X-ray for electron lasers. So I guess we'll go back to EM. And so the wavelengths that we work with are quite different than X-ray. So with X-ray crystallography, I guess the standard wavelengths are on the order of 70 or 150 picometers, depending on the source. I'm not depending on the source, depending on the collimation of it. So, but on EM, we're much smaller. So even on an 80 kV microscope, the wavelength is 4 picometers. 200 kV is 2.5 picometers. 300 kV is 2 picometers. So we're basically well below the diffraction limit of electron. I mean, well above the diffraction limit of electron. So as you know from earlier, the wavelength of electrons is tiny compared to the resolution that we want to get. So we don't have to. So that's not a problem, even on the lowest end microscope. And it turns out also that collecting a diffraction pattern is quite easy on electron microscope. So this is sort of the normal imaging condition where you have your electron beam coming down, it's hitting the sample and getting scattered or not, and then there's in the back focal plane you get kind of a diffraction pattern, and then things get focused down to the imaging plane, and then get magnified by a series of projection lenses, and eventually you get a picture here. And in the diffraction in the back focal plane, you have an objective aperture to get rid of perhaps highly scattered beam to sort of increase the contrast a little bit. And just about every microscope I've used has a button on it that says diffraction. So you don't have to do very much. You just hit the diffraction button, and what it does is it sort of replaces the projection lenses. Go back up. With a diffraction lens, and so then what happens is you end up, it sort of magnifies one of the crossover points to sort of, so that instead of the real space image hitting the detector, what you get is an image of the diffraction pattern hitting the detector, so you can collect the spots directly, assuming the scope is set up right and everything is focused right. So you do have to make sure the diffraction focus is right, so that you will actually get a finely focused diffraction pattern on the detector. Now, one difference in this mode of images is normally you don't have an objective aperture in it because you want to get all of the highly scattered beam. You don't want to limit it because in this case you really do want all of these 1 angstrom diffraction or less spots. But you do it. But what you do is you put in what's called a selected area aperture, and that's an aperture which is down below in the image plane before it's magnified, and before it would be magnified by the projection lenses. But it basically limits the area that you see, because usually you're illuminating a much larger area than the crystal itself. So the crystal is small, and then it's sitting on a piece of carbon. But you don't want to collect the diffraction of all the junk, all the carbon around the crystal. You just want the diffraction pattern of the crystal itself. So you sort of limit it in real space so that you're only sort of seeing a circle around the crystal. And then when you collect your diffraction pattern, you only see the diffraction of this little part and not the entire field of view. The other thing that you have to insert always is a beam stop. So similar to X-ray, most of the beam is undiffracted, and so you get, in diffraction mode, you get an incredibly bright spot, and that will very quickly burn the detector if you're using an electronic detector. If you film, you would just saturate it.
Even a CMOS will burn out?
The TEATS one is, well, the TEATS, yeah, I guess the non-direct ones are less sensitive, but I wouldn't want to keep collecting diffraction patterns on it all day. I think eventually it would probably not be so good for it. For the direct detector, I mean the direct detectors, they're also CMOS, and they would burn it.
Yeah, those I know, but I thought the CMOS did have an ability to absorb it. Not enough,
yeah, well, I know, like the non-direct one, the TVIPS one, it's okay without it. We have collected without using a beam stop a little bit. I did it with Matthias, but generally, I think it's probably better to. I wouldn't feel good about continually hitting it with this bright spot. And but on the direct detector, like the K2, it would wreck it.
Yeah.
And it's a CMOS, but it's like a bare detector. There's no scintillator. And we've also done it on the DE camera. That one also, we saw it was sensitive. It did recover, but don't collect the diffraction on the direct detector. So, as I said, there's different modes of collection. You can either sort of collect with continuous rotation, or what was originally done, you collect just one spot and then rotate it a little bit. And again, it's the same sort of thing. You want continuous rotation in order to fill in all of the diffraction and collect all of the images and not have, and so that you don't have missing spots, and you make sure that your intensities are actually accurate.
So nice illustration. Did it come from a paper?
Yeah, I forget which one. I think it might have been that review.
It's cute.
Oh yeah, the other thing with difference between electron diffraction is you still have a missing wedge problem. So with X-ray you can rotate the crystal 360 degrees, but in a microscope you're limited to about minus 70 to plus 70 at the absolute most. Probably minus 60 to plus 60 to be safe, but you can only tilt it so high. Again, similar to tomography. And so what you have to do is actually what's been done is merging data between different. You collect several crystals. Ideally, the crystals are lying in random orientations on the grid, and so then that fills in the space. Something else to worry about is the crystal thickness. So this is really only made for fairly thin crystals. If the crystal is too thick, there could be several problems. You could get diffuse scattering if it's not very well ordered, and that would be one reason to be using MicroED is you have a crystal that's not very well ordered, but then you image one little part of it, and hopefully that little part is ordered, or the order might be a little bit different within it. Second thing is inelastic scattering. So as the electrons are going through it, they could get inelastically scattered and then sort of lose energy, and then that will sort of give sort of background, and also give an error in the intensity levels that you get. Or if you get double scattering effects, that also is not good. So ideally, all of the assumptions are that when the beam is hitting it, you get at most one diffraction. It sort of is reflected once and not twice, because you can't sort of keep track of more than one. And so in the original paper, they found that for lysozyme crystals thicker than about 500 nanometers were unusable. So, and I guess ideally they're around 200 to 300 nanometers thick. So for what to do if you do have large crystals is basically try to break it up in solution. So they have several techniques. They use, I think, high frequency sound, or just kind of grind it up by pipetting up and down and kind of crush the crystal that way and make them small enough, or image only the small broken crystals that end up being on the grid. So you end up getting a little, instead of imaging sort of this big, ugly multiple crystal, you end up imaging just a little crystal fragment and you get a better diffraction pattern. So to get into some of the details of what's actually done is the screening for crystals is quite simple because it's sort of like screening for regular X-ray crystals. You can do it by microscope, and in this case you can, I guess they usually just screen for precipitate, or the tiny precipitate. They don't have to be visible as crystals, because if they're visible as crystals, chances are they're good enough for X-ray crystallography. But if they're just sort of fine sort of precipitate, you sort of put that drop, put it on an EM grid, blot it the normal way, and plunge freeze it. Set up your microscope for low dose diffraction and screening, and then collect an initial diffraction pattern of a crystal once you find one, and then if it's really good, collect the whole tilt series of it, a whole diffraction series of it. So ideally, I guess again, you would screen by negative stain for crystals, plunge freeze. Make sure your scope is set up for diffraction. Get it eccentric. Sort of screen at low mag to find crystals, and then set up your dose to be very, very, very low. So 10 to the minus 6 electrons per square angstrom per second. So it's an extremely low dose. Because you're getting these super bright diffraction spots, you want a very, very low dose as you're collecting the images, otherwise you'll saturate the detector. And that actually can be a challenge, getting things set up well under, you're at spot, on an FEI scope, spot 10 or spot 11, so the absolute smallest spot size, so you're getting the dimmest beam. Originally what they did, they sort of were examining crystals, actually staying in diffraction mode the whole time, and then they would sort of use an over-focused diffraction mode, which gives you kind of an image instead of a diffraction pattern, and that way you're keeping the lenses all more or less the same, and then you're still getting fairly high contrast imaging at a fairly low dose. make it eccentric, set up your diffraction beam and put in the beam stop. Set the dose rate to be quite low, say 0.01 to 0.05 electrons per square angstrom per second. Beam of 5 to 10 microns in diameter and no objective aperture, and then insert in a selected area aperture, which is about the size of the crystal that you're going to be imaging. And then collect an image. If you see high quality diffraction, collect the tilting data set. In the original paper, they did single images, kind of like tomography, where they did 0.5 degree to 1 degree increments, and they were able to use just a regular CMOS camera, not a direct detector, but an indirect detector. So it has a scintillation layer to make light. But because of the UL sphere, most of the reflections were only partially recorded. So the fact that the wavelength of the electrons is so small, because the UL sphere is an inverse space or Fourier space, the radius of it is very, very large, so it's almost flat. So that's why we normally don't worry about it for single particle EM until we get to very high resolution, because we don't have to worry about this sort of distortion that's actually happening. But because it's sort of so flat, most reflections are sort of only partially recorded, especially if you do individual ones. And so you have to sort of figure out what the actual intensity is, because you're only getting partial intensities for a lot of them. So if you don't really know, you can't be as confident as you would like to be for your intensities. And so they needed special software to sort of figure out, to sort of solve the structure. And they originally, when this was originally published, they did lysozyme on a 200 kilovolt microscope with a TVIP CMOS detector at 2.9 angstrom resolution. But they needed a lot of their own in-house scripts to index the data and sort of get everything right. They had to also take a whole bunch of images of different crystals in order to fill in space. And these are the original. This is from the original paper where they did it. These are what the crystals look like by eye. With the actual, they were not imaging these crystals. These ones would be big enough for X-ray, but these are the crystals. These are the size of crystals that they're imaging by EM. And then here this is what it looks like in the microscope. So this is 1 micron, and this is probably this is a 2 micron. They also figured that the critical sort of total dose that it could take was about 9 electrons per square angstrom. So beyond that, the sort of data quality drops. So you do have to. They did get a good measure of how the different resolution rings drop according to dose. So definitely, I mean, this is also informative for single particle. I mean, really, only the first few frames of a single particle image have the highest resolution information, and this sort of, I mean, the experiments that they did from MicroED kind of proved that. So this was a sample of one of their diffraction patterns. This is the auto indexing where it found the spots, and this is the beam stop going through, and this is the whole sort of diffraction pattern. So here it goes. This is the movie going through it. So this is, as the crystal rotates, the pattern changes. Say that again, maybe.
So each of the blue squares is a reflection?
Yeah, each of the blue square, yeah. You can only see them by eye. You can only see some of them by eye, but sort of the software auto indexes it and then figures out where it should be collecting the intensities. And then this sort of shows that, you know, small changes in, basically very, very small changes in tilt vastly changes the intensity. So these are this is at minus 0.1 degree, 0 degree, and then 0.1 degree tilt. And so you get a partial peak here, you get kind of a full peak here, and then another partial peak. So it kind of demonstrates that you really, if you're collecting single images, it's hard to rely on what the intensity actually is, because chances are you're only getting one of these partial reflections for a lot of them. For some of them you'll be getting full reflections, but you won't really know what the relative intensity of everything is when you try to combine it. So a better data collection technique is continuous rotation, where you rotate the stage at a continuous rate, a slow rate, and then collect as you're going. So for this though, what you need is a special camera that has what's called a rolling shutter mode. So what the camera is doing is continually, the beam is on the entire time, and the camera is continually reading out. So you're getting image after image after image after image, and so that way you're not really missing any information. You do have to do it at a fairly low rotation rate still to be fast enough for the camera. And so not all cameras have this rolling shutter mode. I know that the TVIP's F416 camera has rolling shutter mode. The CETA, the FEI CETA detector has rolling shutter mode. The DE has rolling shutter mode, but it only lets you collect for a certain amount of time before it sort of runs out. So that's something to consider, because not all cameras have this sort of fast collection mode. We've tried collecting it without rolling shutter mode, and then unfortunately you end up taking a few seconds for every image. So you end up, even though you're doing a very slow continuous rotation, you end up missing wedges in Fourier space as you're collecting. Most of the microED collected has been collected on a CMOS camera in rolling shutter mode. And so when you actually get it, you have to try to process it. When you get kind of a movie of it. You have to tell it where the beam center is, which may not be in the center of the image. So that depends where you centered the diffraction spot electronically. So that could change. That'll change a little bit from day to day, or from experiment to experiment, quite likely. You have to know the rotation rate of the stage, so that you can estimate the angle and the range of each frame. And obviously whether you started moving clockwise or counterclockwise. And then you also need to know the sample to detector distance. So you have to have calibrated your image at your diffraction images, so that you know what the resolution is in Fourier space.
So what software would you use? Crystallography software?
Yeah, actually, apparently there's free software available to convert these sort of movies to this SMV format, and that can be read by Dials, Mosfilm, or XDS. We've also tried from HKL 2000, but then you have to define your detector. We weren't sure how to do that. So you have to sort of you have to be able to define your detector, and the software has to also be configured for electron diffraction instead of X-ray diffraction. So it needs to know the wavelength and all of that. And these three ones, definitely there are configurations to get where it will work.
And the calibration of...
that's actually not so hard. So you actually I'll have a picture of it later, but you just have gold pattern sputtered onto a grid, and it'll automatically sputter into little microcrystals of gold, and then the spacing of gold is well known. So
and you need to do it once, or
you should be able to just do it once, yeah. So you can't just you do have to do it. You do have to calibrate it yourself, like with a real diffraction pattern. You can't just sort of base it on measurements like you would with an X-ray, where you physically know how far the detector is from the source. But in this case, because everything gets magnified, you sort of have a virtual detector distance rather than the actual physical distance. So you also have to, there are further complications where you have to make sure that, the gain is okay, the sort of, what the meaning of the relative intensities and all that are sort of well understood. The camera also doesn't, at least the 416 camera doesn't label hot or dead pixels, so you have to be aware of that in the swirling shutter mode. And you have to collect it at a very low dose so that even the strongest low resolution reflections are still within the linear range of it. And so you need to, and finally for the software you have to be able to configure what the camera length is, the wavelength, and where the tilt axis is. So you do, I think you do need someone, or ideally someone who has some background in processing these. I think ideally you would work with someone who's got X-ray crystallography background, who already knows the software well, and could then help configure it for your hardware and for your experiment. So the indexing, I went to Tamir Gonin gave a course. Actually, he gives a course I think almost every year, and I went to it at Genelia, I guess almost 4 years ago, and he was using MOS film at the time, and that seemed to work pretty well, where it would sort of, we collected at 200 kV, and it was able to index, the auto indexing worked pretty well, and it sort of, we were able to do lysozyme without too much trouble. It took it was like a 3 or 4 day long course, but I would recommend if you want to do it, you should look up when he's giving his course next. He's now at UCLA, but he gave a very good course on how to actually do this. They sort of, for the various errors, they sort of use this mosaicity term to sort of absorb sort of residual errors. So it wasn't a real mosaicity error, but any sort of error would sort of get junked into this thing that they called mosaicity of the crystal, so that it would sort of work. It would sort of act as a sink for problems with it, with any sort of crystals. But it all worked out somehow. The phasing for protein structures it's pretty much always done through molecular replacement. So because you can't. There's been no technique to do heavy atom derivatives, or there's no anomalous diffraction that anyone's been able to do for ED yet. So they sort of have done have for larger proteins do all the molecular replacement, and then for small molecules it's been done by ab initio. And then you sort of, in a way, once you've sort of done it, it becomes a very similar experiment to X-ray crystallography, where you have sort of a standard table as to how complete the data is, and the lattice parameters, and all of that. And then here's another, this is just a sample of the sort of resolution you can get, which is extremely high resolution. Actually, I think that you can sort of, I think they're at the point where they can kind of see hydrogen atoms in the highest resolution structures. These are sort of the hydrogen atoms. So if you have a really small peptide or something, you can go to and you get nice little crystals of these sort of microcrystals of it. You can get actual resolution down to sub-angstrom. For thick crystals, actually, there's been a couple of papers recently where they sort of propose actually using focus ion beam milling to actually make them thin enough for microED. So one was by Tamir's group, and another group was this group in China where they did the same sort of technique. Basically, you have this is an image from, this is all from Tamir's paper, but they sort of freeze crystals onto a grid in the normal way. So you blot your solution onto the grid, freeze it, and then these crystals are all big. So this is the view from the SEM beam, and then this is the view from the ion beam. Where, if you remember from the fib lecture, when you're sort of viewing it with the ion beam to sort of mill lamellae into cells, you're sort of viewing it almost along. You're sort of viewing it almost along the grid axis as opposed to right above it. So you're sort of looking on it like that, at an angle like that. So then they chose this crystal, which is kind of big, to make smaller. So here it is zoomed in again, looking at with the ion beam, and then they mill away the top and bottom of it, which was done here, and then they leave a little lamella of crystal. So this, what was this pyramid crystal, now it's all you have is this little wedge, and then it's being held up by what was the base of the pyramid. And so this is now, I think, about 300 nanometers thick. And then here it is after it's been thinned, looking at it from the top view with the SEM beam, and then they put it into a TEM, and this is what it looks like in the TEM. So this is again the thin crystal. It looks a lot wider because instead of looking kind of edge on almost, you're looking at it straight up and down. And then you can you know, you can kind of find these pretty easily because they're pretty obvious where you've blasted away most of the grid area with the ion beam. And then they solved proteinase K to 2.7 angstrom resolution. This didn't actually go as high as what they get from the microcrystals, so they were sort of suspecting it's perhaps the gallium beam did damage it a little bit or something like that. They didn't see any ice diffractions, so it didn't seem to cause it to recrystallize, but it still didn't go quite as high as they got from the tiniest crystals. But it worked. And so this would be another, if your crystals, I guess, were a little too big for microED, but still too small for X-ray diffraction, you could use this. I mean, obviously this technique has a lot of disadvantages in that you need a whole other microscope, and it kind of, you then have a lot more complications, because in order to even do this is a lot of work, but it's a possibility. So in 2018, this technique became kind of a breakthrough because they sort of realized, I think Tamir said he was talking to some colleagues in the chemistry department after he moved to UCLA, and sort of realized he realized that they could actually use this on a small molecule, like not proteins but actual things like drugs or really small organic molecules. And so the advantage of that is you could put purified powders directly onto an EM grid, dry, not in solution, and so then you don't even have to plunge freeze it or anything. You just put a powder of your sample on a grid, and you can even do it at room temperature if you wanted. We've done that. I guess ideally if you did it at cryo, it should be a little bit better protected, but still, you can put multiple samples on one grid, and each crystal collection is kind of pretty fast because it only takes a couple of minutes. Even though you're rotating slowly, it takes a few minutes to do it. And then they're small enough to be solvable by direct phasing methods.
So if you put a powder on a grid,
yeah,
how do you make sure it stays?
I think basically what we did is we sort of dipped it into a very fine powder of a pill we ground up, and then kind of waved most of it off, and only the tiniest thing, only the small things will stick to it. It's kind of stuck. All those small things are stuck to it kind of by van der Waals forces. And so the bigger stuff should just kind of fall off naturally, and only the tinier things will stick. And they seem to stick pretty tightly.
Even in the vacuum?
Pardon?
Even in the vacuum?
Even in the vacuum, yeah.
There's no vibrational motion of the crystals?
No, they seem to be stuck, when they're stuck to the grid, I think when they're so small, they're stuck very tightly to it. They just sort of, basically by van der Waals forces, so that when things are really small, kind of gravity and other things don't have such a large effect, but these forces become very large relative to the amount of other forces on them. So they published this paper in 2018, the Cryo-EM, this method for small molecule determination. And so what they did is they just sort of they started off with some sort of standard lab chemicals. This is progesterone. This is an EM grid. They put it on an EM grid, and then did their microED of it, and collect. That took about 3 minutes of collection. Of course, they would have had to search for it and set up the microscope, so a little exaggerated there, but still, they could collect a full data set from one crystal in about 3 minutes. And then in terms of calculations, I guess once you know what you're doing, the calculation isn't that hard. Certainly, it's not like you need, like for a single particle where you need a cluster or a lot of GPUs to solve it. The diffraction pattern solving is not as computationally expensive, so they could solve in about 10 minutes, and they got an atomic a 1 angstrom resolution structure of it. And then in this paper, they did a whole bunch of different things. So basically, I think they sort of took a bunch of chemicals they found in the lab, and so acetaminophen, ibuprofen, biotin, and then solve structures of it. Because these powders, I guess, are actually microcrystals of it. And we're trying to get it going at NYSBC. We don't have a full workflow yet, but we will soon. We're trying to work it into Leginon. But we did the same sort of thing with caffeine. We just ground up a pill and then kind of dipped a grid in it, and a lot of the little things stuck to it. I found that it helped. It was better to use a non-glow discharge grid, although this is just 1 or 2 times. But somehow I think it seemed to be better with a hydrophobic grid than a hydrophilic grid. But I'm not. That's just n equals 1 or 2. And they also, what made the organic chemists excited was they could actually go from basically a Flask to structure. So they had a chemist was making something, and then he sort of freeze dried a film of it into a little beaker using a freeze dry apparatus. Put a little bit of this onto a grid. They did 4 samples, and 2 of them diffracted well enough to get crystal structures. Again, this was really fast. So then I think they're quite excited by the fact that we can go from this to this in a very short amount of time, and using the microscope on site, not having to redissolve this and try to grow a crystal of it and then do X-ray diffraction of it, but just go from the purified or the synthesized molecule to structure and see what it is. What they also did is they also did an experiment where they put several of these drugs onto a grid and solved several structures from the same grid. So even though they didn't know what the crystal was, they were able to use this MicroED method to actually sort of figure out what was on the grid. What's going on now is people are trying to collect on even lower end microscopes like non-field emission guns, so that any microscope in the world almost could work. Fib milling may become more popular for slightly thicker crystals. I don't know. To me, it seems still a very difficult. You're kind of it becomes a lot more difficult if you want to do fib milling of thicker crystals. And they're trying to also make it work better on slower or non-rolling shutter cameras, but the lack of continuous collection complicates the processing. And then it'd be good to add parameters for this to all of the standard X-ray software, so that probably will improve, so that you could then just tell it what microscope and give it some various parameters to sort of just collect. So I guess the advantage of this technique is that you only need mid-level equipment, so 200 kilovolts. FEG right now is probably better, and a CMOS detector with moving on. So this still isn't very, very low end, but it's still not Titan Cryos level end either. So it's mid-level. So we have an F20 downstairs, and that's actually the microscope that the method was originally developed on. Because you're collecting diffraction instead of imaging, the alignment is probably less difficult than for imaging. It should be more stable at least. And it has the highest resolution yet achieved by a cryo-EM technique. The disadvantage is you still have to grow crystals, and the crystals have to be small. And you need a high quality stage where you can continuously rotate it. And you still have the phasing problem. So for most protein structures, you still have to do molecular replacement. And so this is actually this image was collected recently on our Joule 1230. So this is our lowest end microscope. It's an 80 kV tungsten filament, and this is just in diffraction mode with I think a 40 centimeter camera length, and this outer ring is 1.2 angstrom. This is a 1.2 angstrom resolution. So even though the microscope itself will not image to that resolution, so if I take an image of gold, or I will not see a lattice. This is 2 angstrom here. Even graphite on this scope, which is 3.4, I can't quite see a lattice, but because we're not imaging, we're using diffraction modes. The imaging optics don't really matter anymore. and the environment matters a lot less because this is actually because you're collecting diffraction, it becomes insensitive to vibration or sample movement because you're just getting the intensities of it. So any sort of vibration or sample movement would show up in the phases, but you're not collecting the phases. So it actually becomes much easier to collect on a much lower end microscope. So yeah, that's the MicroED technique. So it might be, especially for organic chemists, I think they're quite interested in it.
So when you see rings like that, that's typically different lattice features.
Oh yeah, so the reason you see rings, ideally if it was one lattice you would see spots, but because this is actually sputtered gold onto a carbon grid, and so there's a whole bunch of lattices, and so it's enough lattices that it basically appears almost like a continuous ring. But ideally it would be individual spots all along that ring.
I guess in some of the diffraction patterns you showed earlier, there's the darker halo around. Is that the ice ring, or?
Probably. It depends which. Yeah. So this is there's probably no ice here, so this might be something else.
It was really prominent in the first one that you showed.
Oh. Not that one.
There was some in there.
Oh yeah. This is 3.3 here, so this would be around 4, so this could be an ice ring, yeah. Chances are it is a little thicker around the crystal.
So from a practical point of view,
Yeah.
how would you get started if you have a microscope and
So what we're doing is actually we ground up a little bit of caffeine or ibuprofen on a pill, and then put that on a grid. We sort of dipped it into the powder and then shook it off.
And how do you need to set up? Do you need to set up your microscope in a special way? Or?
Yeah, so to set up your microscope, you should, I guess, put in a carbon grid or actually a cross-grading grid would be good because it's got a little bit of gold sputtered on it. And you could look at it in diffraction mode and make sure that in diffraction mode the rings are round and not oval, because the diffraction mode could be, if the diffraction astigmatism is off, you would get ovals.
Okay.
So you make sure that the diffraction pattern is perfectly round. And I guess make sure that when you go to diffraction, the diffraction beam is set up is right more in the middle, and not off in some funny place.
And do all microscopes have a beam stop?
They all have a beam stop. What you might want is a microscope that has a very small beam stop, so that way you're not really losing the lowest order diffraction spots. So on our F20, it actually happens to have a beam stop which is quite small. Standard beam stops are a little bigger, so they'll sort of block the lowest resolution rings. There'll be more stuff kind of behind the beam stop. So you can imagine it might be a bit bigger than this. But we actually have done it also on one of the cryoses. Angie's been trying to get it to work with Legend on, and so we've collected on the CETA camera on that, because it also has a rolling shutter mode. And on that one the beam stop is quite big, but it still probably is okay.
And like holder, can we just like standard holder?
Yeah, standard holder. We've for the powders we've just been doing it on the room temperature holder. But you could do a cryo holder too if you wanted to do it at cryo temperature, or if you're on something with an autoloader, then there's no problem at all. But you'd have to make sure your goniometer is good, because of this. When you're doing this continuous rotation, you don't want, if the goniometer is not well aligned, like if the tilt axis is off the optical axis, then when you tilt it, it will appear to move, and if it moves out of your imaging, then it won't work. So your goniometer should be good. And you also have to, I think if you want this continuous collection, which seems to be what works best, so you want a camera with rolling shutter mode, so you can continually collect. So the CETA camera has it, the TVIP's F416 camera has it, but some older cameras or CCD cameras don't have it, so then you're stuck taking still images. Are you at Cornell, or are you?
No, Princeton.
Oh, okay. You have a Cryo. I know you have a lot of microscopes there.
Okay, we have a talus, I think, that would be used for that.
Yeah.
People are just starting to think about doing it.
Yeah, so this, if you have the CETA camera on that, it has
Yeah.
rolling shutter mode. And they make a CETA D camera now, which they call for, I guess it's hardened for diffraction too. I'm not sure if it's, how necessary that is, but.
If you're curious, August 11th to 14th of this year at UCLA, Tabir is holding this course. MicroED for proteins and small molecules.
Actually, if you're interested, you should probably sign up early too, because it tends to be overbooked. I think they only take 5 or 10 students or something like that, because they can only fit so many.
Wednesday
Okay.
is
Journal Club.
Wednesday Journal Club. Makeup from treatments or
No, we pushed it back a week. So we were going to be talking about, it's going to be a single particle paper on a structure of the HIV trimer that was much debated in the field when it was published. So we pushed it back a week so that Jay Gorman, who is a postdoc who is embedded here, who works in the HIV structural biology field, can be here and give us a sort of insider's perspective as he was working in Peter Kwong's lab when the structure was published. And people talked about it a lot, and there's a lot of controversy surrounding the validity of the structure. So it's going to be a single particle paper / how do you get 3D reconstructions out of very low signal-to-noise ratio images, and what are some of the potential pitfalls. So it should be a good discussion. It's going to be like 4 or 5 papers that are going to get covered. But we might do a Google Hangout for it. I think that's what we've done in the past. But effectively, yes. Just not through YouTube. But we can send out a link for it.
It's a kind of a weird coincidence. I mean, I forgot to mention in the lecture, but this technique came out almost the same time as direct detectors. Maybe a little bit before, I think. But sort of like at the same time, we had 2 techniques that like suddenly vastly improved EM.
Make sure to send a sign-in sheet if you haven't already. Bill Haynes.
Thank you, Bill.
Thanks, Bill. Bill's last day here is next week.
Next Friday,
So, you guys are lucky. You'll be here for next year's course. Or maybe we can get him to come back.
As a guest lecturer.
As a guest lecturer.
Next year, maybe.
Hey, are you going to go on that pen?
Yes.